Welcome to the session on parametric equations. The objectives for this session are to convert parametric equations into Cartesian form by using substitution. The x and y coordinates of each point on a curve can be written as functions of a third variable. This variable is usually represented by the letter t and is called a parameter. A curve can be defined by using parametric equations of the form x equals p of t and y equals q of t. Every value of t defines a point on the curve with the coordinates p of t, q of t. Let's now take a look at an example. Here's a curve and the parametric equations of the curve x and y. The domain of the parameter t greater than 0 in this example gives information about the values of t which need to be substituted to find the coordinates of the points of the curve. Generally, the value of the parameter t is not equal to the x or y coordinate. So let's take a look at a couple of examples of points on the curve. When t is equal to 3, we plug that in to the function for x. So x equals 3 squared plus 3 all over 3, which is equal to 4. So the x coordinate is equal to 4. And y equals 3 times t, which is equal to 3 times 3, which equals 9. So one point on the curve is 4, 9. When t equals 1, we plug in t equal to 1 in the function for x, which equals 1 squared plus 3 all over 1, which is equal to 4. And y equals 3 times 1, which is equal to 3. So another point on the curve is 4, 3, as shown here. Notice that more than one point on the curve can have the same x coordinate as in this example. By using substitution to eliminate the parameter, we can change between parametric and Cartesian equations. The domain and range of the Cartesian function can be found by using the domain and range of the parametric functions. So for parametric equations, x equals p of t and y equals q of t, with the Cartesian equation y equals f of x, the domain of f of x is the range of p of t, and the range of f of x is the range of q of t. Let's take a look at an example. Pause the video and have a go. Press play when you're ready to view the solutions. Let's take a look at part A first. A curve has the following parametric equations: x equals t minus 2 and y equals t squared plus 1, where t is greater than or equal to minus 3 and less than or equal to plus 3. We are required to find a Cartesian curve of the form y equals f of x. So let's solve this. Since x equals t minus 2, we can rearrange this to obtain t equals x plus 2. We can now plug this in to y equals t squared plus 1 to give us y equals x plus 2 all squared plus 1. Expanding this gives us y equals x squared plus 4x plus 5. And so we have our function y equals f of x. Now let's take a look at part B. Using the same parametric equations, we are required to find the domain and range of f of x, which was found in part A. So let's solve this. Since x equals t minus 2, and t is greater than or equal to minus 3 and less than or equal to 3, if we subtract 2 from the entire inequality, we obtain minus 3 minus 2 is less than or equal to t minus 2 is less than or equal to 3 minus 2, giving us that x is greater than or equal to minus 5 and less than or equal to 1. Since t is greater than or equal to minus 3 and less than or equal to 3, we have that t squared is greater than or equal to 0 and is less than or equal to 3 squared. And adding 1 throughout gives us that 0 plus 1 is less than or equal to t squared plus 1 is less than or equal to 9 plus 1. So y is greater than or equal to 1 and less than or equal to 10. Therefore, we have the domain and range of f of x. And now for part C. Using the same parametric equations, we are required to sketch the curve within the domain for t. So let's solve this. Now from part A, we have that y equals x plus 2 all squared plus 1. We can use this to find the minimum point of the curve. Here's our curve. Let's see where all the points came from. The point minus 2, 1 is the minimum turning point. We can obtain this by putting x equal to minus 2 in this equation. This will make the x plus 2 squared term disappear and therefore give us y equal to 1. Now from part B, we have that x is greater than or equal to minus 5 and less than or equal to 1, and y is greater than or equal to 1 and less than or equal to 10. And so we have our curve stretching on the x-axis from minus 5 to 1 and on the y-axis from 1 to 10 as shown. We can also find the intercept. So when x equals 0, we have that y is equal to 5, here as shown. Now let's take a look at another example. Pause the video and have a go. Press play when you're ready to view the solutions. Let's take a look at part A first. A curve has the following parametric equations. X equals ln of 2 plus 3 and y equals 1 over t plus 5 for t greater than minus 2. We are required to find a Cartesian curve of the form y equals f of x. So let's solve this. Since x equals ln of t plus 3, we can raise both sides to the power e to obtain e to the power x equals e to the power ln of t plus 3. And of course, since e is raised to the power ln of something, we have that e to the power ln of t plus 3 is equal to t plus 3. And therefore, we have that e to the power x equals t plus 3. And rearranging this gives us t equals e to the power x minus 3. We can now substitute this into our equation for y, which is equal to 1 over t plus 5. giving us y equals 1 over e to the power x minus 3, which is replace t, plus 5, as shown. And tidying up gives us 1 over e to the power x plus 2. And therefore we found our Cartesian curve. Now let's take a look at part B. Using the same parametric equations, we are required to find the domain and range of f of x. So let's solve this. Now from part A we have that y equals 1 over e to the power x plus 2. Now since x equals ln of t plus 3, where t is greater than minus 2, we have that x equals ln of t plus 3 is greater than ln of minus 2 plus 3. And tidying this up gives us that x is greater than 0. For y, since we have that y equals 1 over t plus 5 for t greater than minus 2, we can rearrange this to give us 1 over t plus 5 is less than 1 over 3. And therefore y is less than 1 over 3. And therefore we found the domain and range of f of x. This brings us to the end of this session. If you have understood its contents, you should be able to convert parametric equations into Cartesian form by using substitution. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to this topic.